Into the atmosphere, and then 30 kilometers above the ground, it exploded. This violent event was brighter than the sun, but so high up that it was silent for a full 90 seconds after the blast, which only made the devastation worse.
So you see all these videos of people, look at what was that? They see the smoke trail in the sky, and, oh, that's amazing. And then, just when you think nothing's going to happen, the shockwave hits and it blows out the windows. 1,000 people got glass in their face and their eyes because they're looking through the windows.
The shockwave damaged thousands of buildings and injured 1,500 people. What makes the Chelyabinsk incident kind of embarrassing is that the very same day, scientists had predicted that an asteroid would make a close flyby of Earth. And they were right. 16 hours after Chelyabinsk, a similar-sized asteroid, known as Duende, came within 27,000 kilometers of Earth's surface. That's closer than satellites in geosynchronous orbit. But while they correctly predicted this close approach, they completely missed the unrelated asteroid that exploded over Russia. And the truth is, this happens all the time. We're really not that good at detecting asteroids before they hit us. Since 1988, over 1,200 asteroids bigger than a meter have collided with the Earth, and of those, we detected only 5 before they hit, never with more than a day of warning. With all our technology and all the telescopes across the Earth, not to mention the ones in space, why do we struggle to detect dangerous asteroids before they strike? What are the chances that a big asteroid will hit, wiping out most, if not all, life on Earth? And if we saw one coming, what could we do about it? Asteroids are the leftover debris from when our solar system formed. 4.5 billion years ago, rocks and dust clumped together into molten protoplanets. Inside, heavy elements, metals like iron, nickel, and iridium, sank into the core, leaving lighter silicate minerals on the surface. Some of these protoplanets grew into the planets we know today, but many more collided with each other, breaking into pieces. These pieces continued orbiting the sun and smashing into each other and breaking into even smaller fragments. These became the asteroids. Most of the asteroids have stable orbits between Mars and Jupiter in the main asteroid belt, but some have made their way closer to Earth, and these are known as near-Earth objects. They are of greatest interest to us because of the threat they pose. In his last book, Stephen Hawking considered an asteroid impact to be the greatest threat to life on Earth. But finding asteroids is difficult for several reasons. Most are spotted by ground-based telescopes.
So what you do is you take a sequence of pictures, 1, 2, 3, 1, 2, 3, 4, and you look for essentially a moving dot. And it's moving because it's orbiting around the sun, whereas the stuff far away, the stars and galaxies, are not.
But you have to look carefully. Asteroids are not very big. They range from meters up to kilometers in size. And in the vast expanse of space, rocks like that just don't stand out. And even the small ones can be damaging. The Chelyabinsk meteor was only around 20 meters in diameter, roughly the width of 2 school buses. Plus, asteroids are rough and dark. They only reflect around 15% of the light that hits them. So our best chance to see them is when they're fully illuminated by the sun. And that's why over 85% of the near-Earth asteroids we've detected were found in the 45 degrees of sky directly opposite the sun. Even once you've detected an asteroid, it's hard to tell if it will hit the Earth.
So if you just discover an object and you only have data from a few days, then you can't really tell where it's going to go because you're trying to take this little arc of motion and predict it far into the future. So what you need is observations over years and years. But even if you have perfect observations of an asteroid, there's kind of a fundamental limit to how far in the future you can predict. And that's because a couple of effects. But one is that, they're not just orbiting the sun with no other influence. All of the planets have gravity, and all of the planets are pulling on near-Earth asteroids and can change the orbit significantly. So there is something called dynamical chaos, which basically means after a certain amount of time, you don't know where the asteroid is going to be. And in practice, what that means is we can't do any work more than 100 years in the future. So the maximum time you can predict with any accuracy at all where a body will be is about 100 years.
And this is pretty important, because we know with certainty if one does hit, the results will be dramatic. This is Barringer Crater in Arizona.
An impact at high speed is not like you're throwing a stone into a brick wall, and it makes a hole and sticks in there, or just bounces off. It's explosive. It's like totally explosive. So the kinetic energy of the projectile comes in maybe 30 kilometers per second. The kinetic energy of the projectile is big enough to completely vaporize the projectile. It turns it into a gas. And that gas is super hot and super high pressure. And it explodes, and it blows out the crater. So the projectile doesn't really exist after the impact. I mean, little pieces can survive. But this 50-meter body was basically obliterated.
The 50-meter asteroid, not that much bigger than Chelyabinsk, released the energy equivalent of 10 megatons of TNT. That's over 600 times the energy of the Hiroshima bomb. So the thing that most closely resembles a meteorite impact is a very large nuclear explosion. What are our chances that Earth gets hit by another 10-kilometer or bigger asteroid?
In your lifetime, assume you live to be 100 years old, you have a 10-kilometer impactor like the KT extinction event every 100 million years or something like that. So the probability of getting it in 1 year is 1 in 100 million. So you have 1 in a million chance of dying from a 10-kilometer impactor. But because we know that there are no 10-kilometer impactors with a path that intersects the Earth for the next 100 years, your chance of dying from that is actually 0. So work done already has reduced that down, from 1 in a million to nothing.
So the good news is there won't be another dinosaur-style extinction event in our lifetimes. But there are exponentially more asteroids of smaller sizes. For every 10-kilometer asteroid, there are roughly 1,000 1-kilometer asteroids, and they're still capable of doing a lot of damage.
4 billion years ago. This computer simulation has been made with the scientific advice of geophysical experts to show the effects if the impact were to happen today. The asteroid's diameter is larger than the main island of Japan. Even though it is moving at over 720,000 kilometers an hour, that's almost 450,000 miles an hour, the asteroid appears eerily slow because of its size. The actual impact happens in the Pacific Ocean, just under 1,000 miles south of Japan. crust of the Earth is peeled away like an orange skin by what is called the crest tsunami. Even the deepest part of the Pacific Ocean looks like a thin film. Huge chunks of debris the size of city blocks are hurled into the air. The entire Japanese archipelago is disintegrated, as is some of the Asian continent. The shattered remains are hurled out into space way beyond the atmosphere to bombard the Earth with deadly intent when they re-enter. At 7,000 meters, 23,000 feet, the rim of the crater is higher than many mountains on Earth today. The size of the crater would be a distance of 2,500 miles or 4,000 kilometers. And this is just the start. And the expanding wall of vaporized rock reaches the mountains of the Himalayas. The perpetual snows are instantly evaporated. Soon the wall of fire reaches the Amazon, the furthest distance from the point of impact. The forest spontaneously combusts even before the rock vapor arrives. Just one day after the impact, the entire planet is covered. Every living plant or creature is vaporized. It's been estimated that this vapor would cover the entire globe for almost a year. It would be as if the sun had come to Earth. The ocean would start to bubble and boil. And as the water evaporates, the oceans would drop at the rate of 5 centimeters or 2 inches every second. Even the salt deposited on the ocean floor vaporizes, and then the very bottom of the sea melts. Nothing is left untouched. One month after the impact, the surface of the world has been sterilized. The oceans have vanished. All that remains is the superheated bedrock.